Hi everyone, we're going to start the second and third law of motion notes today. So turn to OP64 and write the title, second and third law of motion ECQs. And write down the 3 ECQ questions. I'll read them out loud for you, and you may pause the video anytime, as we've always had in the past. Number 1, explain the relationship between force, mass, and acceleration according to Newton's second law. Number 2, describe how to use the force triangle to solve for force, mass, and acceleration. And number 3, illustrate an example of Newton's third law. Use arrows to label the action and reaction forces in your example. Go ahead and pause your video now so that you can write this down before continuing. On page IP64, if you have not yet already, please go ahead and title this ECQ Answers. You want to number each answer so you have a spot for number 1, 2, and 3, and leave spaces for each answer. We'll come back and answer this at the end. Okay. When you're ready, go ahead and continue. Title page IP65 as Newton's second and third laws of motion. You can set up Cornell Notes on IP65 and set up a key for your highlighters if you like. You should be using highlighters to highlight vocabulary, definitions, and key facts. Continue when you're ready. The essential question for our notes today is, how do we see Newton's second law and third law of motion happening in our daily lives? Newton's 3 laws of motion are fundamental for physics, and so they're real and everywhere. So once you learn these, hopefully you can see how it's happening around you. Number 1, Newton's second law. A, force equals mass times acceleration, or F equals m times a. This X sign right here is a multiplication sign. Okay? And this is a mathematical formula that you'll have to memorize. We'll put this in a force triangle later. B, more force is needed to accelerate an object faster. Okay? That means if you want an object to go faster, you would just have to use more force. So for example, if you want a car or a bicycle to go faster, you would have to pedal harder or step on the gas. Okay? C, if the mass is bigger, you will need more force to change its motion. That means the larger the object is, the more force you need to make it move, or speed up, or slow down, or stop, or change direction. So for example, if you're kicking a soccer ball, okay, it's not too bad, you can just use a little bit of force. But if you had to kick a bowling ball, you would have to use more force because its mass is bigger. Later this year, you'll be building rockets. If you build a rocket that's really heavy, you're going to need more force to move it. If you build one that's light, you would need less force and maybe it can go farther. D, the force triangle. Just like the speed triangle, we'll be using this to help multiply or divide different variables of force to calculate each part. Oh yeah, I forgot something. Go back one. These two are your answers for ECQ1, so by the way, you might want to write in your notes ECQ number 1 for letters B and C. This will help you out later. Right? The force triangle, this is for ECQ number 2. Okay? So in the force triangle, label force, mass, and acceleration where they belong. Include the mathematical symbols. Between force and mass you divide, and between force and acceleration you also divide. Remember the bottom variables on the bottom, mass and acceleration, you would multiply. Force equals mass times acceleration. Right? To calculate mass, you would take force divided by acceleration. And to calculate acceleration, you would take force divided by mass. Right? And that's your answer for ECQ number 2. Let's not forget our units. So your units for force are newtons, represented by a capital N, which is actually made of kilograms times meters per second squared. You don't have to worry about that too much. Just remember the units for force are newtons, and you might want to highlight that. The units for mass are in kilograms, and the units for acceleration are meters per second squared. A shopping cart simulation. Let me show you online a little example. Okay, but before we start, just so you see what happens, this is how much force each person can exert or put onto a shopping cart. So like this person can push only 10 newtons of force. This person will push at about a rate of 20 newtons per 20 newtons. And this larger person at the very bottom can push with about 40 newtons of force. Okay? And then there's also different masses of shopping cart: a smaller shopping cart, middle shopping cart, and a heavier shopping cart, right? To calculate acceleration, we either take force divided by mass, like the triangle says here. Acceleration equals force divided by mass. Okay? So you're going to figure out how fast these people can accelerate or push with their shopping cart when they're pushing different shopping carts, depending on how heavy they are. Okay? Are you ready? So let's go online. Let's see, there it is. So here we are online, and if we chose, for example, the smaller person, which has a force of 10 newtons, and a small shopping cart, which will have a mass of 10 kilograms, you would divide those two, which would give us an answer of 1 meters per second squared, and that's her acceleration. Zoom, with a shopping cart. Okay? But you can try giving her a heavier shopping cart, so 10 newtons, and a mass of a heavier shopping cart. And if you click go, 10 divided by 40 gives you 0.25 meters per second squared. She's accelerating much slower, right? And an example could be the strongest person here pushing the lightest shopping cart. What do you think is going to happen? Right, 40 divided by 10 is going to give you 4 meters per second squared, and whoa, there he goes. Okay, and you can play with this online. The link up here, copy, see this in blue, will be on your Haiku page. Actually, yeah, I'll post a link online. You'll be able to play with it. Okay, let's continue to the next part. So continuing on. Stop and make 2 questions using the following question terms: state, define, describe, explain, and how. Remember, there's no repeats, and of course we don't use what questions. When you're done, go ahead and continue. Number 2, Newton's third law. For every action, there is an equal and opposite reaction. This is probably the most famous law out there. Equal means equal in size, and opposite means opposite in direction. Kind of like how forces are balanced. Forces always act in pairs, actions and reactions. Okay? So this rocket can go up because it's pushing on the floor, and the floor helps push it back up. Stop and make 1 question for Newton's third law, and use the following words. Choose any one of these, but do not repeat the 2 that you already chose earlier. When you're ready, continue. And here are some examples of the third law. You do not have to write these examples down, but read through them or follow me to see how the action forces are different from the reaction forces. So some other examples, just remember that every action and reaction pair have equal in magnitude or strength and opposite in direction. So like Dora and Boots giving each other a high five is actually an example of the third law of motion. Another example is a rocket blasting off to space. The action is the force of the hot gases from the rocket exerting an action down on the ground, and the reaction is the ground putting a force back up on the gases and the rocket to launch it up. It goes up since the Earth is bigger and is able to withstand the rocket's force. Right? The rocket's not going to destroy the Earth when it pushes up. Okay. A high five again, like I mentioned with Dora and Boots. High five, if you give somebody a high five right now, you'll notice that you'll be putting an action force on that person, but you do feel a reaction force in return. Even if they did not move their hands, your hand feels something because there is a reaction from their hands. Okay. When you exert a force on something, no matter how big or small, it always exerts an equal force back. So when you push on an object, that's your action force here. The reaction force is the object pushing back on you. Again, you feel resistance, you feel that inertia a little bit. That's the reaction force. Hitting a ball with a bat is the same thing. The bat hits the ball with action force, and in reaction, the ball, will also exert a force back on the baseball, and you can actually feel that, especially if you use a metal baseball bat. You can feel the zing in it. Objects resting on a table. Simple, but same thing. A book sitting on the table has an action force pulling down on the table by gravity, right? The table reacts by pushing back up to support the book. And so therefore the book doesn't fall through the table doesn't break, and the book is not floating in the air, it's just staying on the table. Newton's cradle is also another great example. One ball bearing, that's what these little balls are in the middle, exerts a force on the rest. And the reaction is a reaction force of equal size is exerted from the last ball bearing back onto the first ball bearing. So if you use one ball and drop, one ball will fly up and push back and continue. If you use two balls, then two of them are going to fly up, three are going to fly up, and so on, right? Equal but opposite direction. For your summary, write 3 to 4 sentences and use and highlight these 8 words. Yes, you do have to use them all. There are 4 words about Newton's second law and 4 words about Newton's third law. Number and highlight your sentences when you're done. And that's it for our notes. Thank you!